So last time I tried to explain you the shells of quadratic forms. So we are investigating currently the motifs of anisotropic quadratic forms, so anisotropic quadrics. Well, so I try to formulate a result of Vyshek. So let me draw first a picture to illustrate these results. Well, at the same time, also 13-dimensional quadratic form, so 14 Tate motifs. Quadric is 13, and so this splitting pattern is let it be 3, 1, 2. This is I1, I2, I3. Just an example. So this means so the first shell consists of 3 Tate motifs, and we do the same on the right, then 1, the second shell, and 3. So this is the middle. So it's number 3, number 3. Well, so this is a subdivision into shells. So Vyshek's result in general tells us the following. Well, so before formulating it, so the following trivial remark. So assume that n is a direct summand of the motif of Q. So yeah. So then, so everything is over our base field K. So what happens when we extend our scalars? So if we pass to an algebraic closure of n, so then n will split into a sum of Tate motifs. And we can represent these Tate motifs looking at this picture. So this has a diagram. So for instance, if here will be z plus z shifted by some number, I don't know, then this will correspond to this point, and well, so I can look exactly at the example. It will be actually it will be 11. Well, actually, this is impossible, but assume this happens, then this is this point. Well, we count from 0. So 0, 1, well, 0, 1, 2, 3, 5, 6, 7, 8. Well, so here's the dimension. Well, and then, so we can visualize motivic decompositions of the motif of Q on these pictures. So just saying which Tate motifs belong to which summands. Okay, this is what we will do. So, and Vyshek proved the following statement. So if n is an indecomposable direct summand of the motif of Q, which starts in the shell number E, well, so there are two shells on the left and on the right. I mean, well, so it's convention say on the left. So it's always difficult to tell where it starts and where it ends. So left and right. So if it starts on the left, then it ends also in the shell number I, but on the other side, on the right. And moreover, so one can shift n inside the shell number I. So it means n, so n shifted by 1, n shifted by 2, and so on, are also direct summands of the motif of Q, as long as these shifts remain in the shell number I. So as long as we don't go to the next one. So if they start in the same shell. Well, the key word here is if, because there is no guarantee that there is an indecomposable direct summand which starts in the shell number I. So maybe there are none. But certainly for the first shell, there are. Because so here is the leftmost Tate motif with shift 0. So it should be something starting from there. So and applying it to the first shell, so it should start here. Well, there is definitely someone starting here, and then it should end here, somewhere here. But still, we can shift inside the first shell. So we can always shift it to here and then to here. Not anymore, so this will be out. Then we have no choice. So this point should be connected with this one, with number 11. Well, and then we shift. So let's draw it like this. So this is connected to this, and this to this. So then the same for the second shell. So, but if there is a direct summand which starts here, it must end here, also in the second shell. So then it looks like this. So every indecomposable direct summand which contains this Tate motif over the closure must contain the other one. And here also the same, like this, and like this. So we get such a picture which gives us, well, pretty strong restrictions how the motif of a quadric can look like. Okay. Well, I don't say it is a complete Mathivic decomposition. So moreover, I'm not sure that such a quadric exists at all. Maybe there are no quadrics of dimension 13 with this splitting pattern. So, well, it is known, but I don't know it now, whether it exists or not. So we have at least these connections, maybe more, but at least these. But actually, well, yeah. So there is this binary motif theorem which gives further restrictions. So the answer is there are more connections. There must be more connections, but so let's skip it for a moment because it's well. So now let us apply this principle to an extreme case when there is only one shell. So let us take so either a Pfister quadric or maximal Pfister neighbor. So this is the same as codimension 1 subquadric. Well, then there is indeed only one shell. So the first, say anisotropic as usual. So then I1 equals the maximum possible value. So dimension of the respective quadratic form divided by 2. So it's maximal possible value. So there is only one shell. So the splitting, this splitting pattern consists just of one number. So so let's take as an example a threefold Pfister form. So then it will be a 6-dimensional quadric. Well, and so this is a subdivision into shells. And then we have the following connections, like this. It's the only choice. And then we are able to shift this motif inside the shell. So let's shift it just by one. So then this is connected to this to this, and this to this. So we get such a decomposition just automatically for Pfister quadrics. And actually, what we see here, it's a Rost motif. So this famous motif from the proof of the Milnor conjecture. So you see, it follows just formally from this from the Vishek's from these methods of shells. Well, and in this case, it's indeed a true decomposition, just because, I mean, by combinatorial reasons, there is no other way to arrange connections. So they can't be connected with each other because they are in the same shell, and then it's not. It would not be possible to shift. Well, so nevertheless, so this is of course much simpler than this statement, and so it's not so easy to find an easy proof in the literature. But so I know one, so I would like to tell you. So a very simple, very short proof of this decomposition for n-fold Pfister forms. How one can get this decomposition, in particular, how one can construct Rost motifs in a pretty elementary way. So it will be a theorem of Rost. So that if Q is, so let me do just the Pfister case. So it's even dimensional case, so maximal Pfister neighbor. It's odd dimensional case. So let me do the most complicated one. So let Q be an anisotropic n-fold Pfister form. Our base field, or maximal Pfister neighbor. So dimension of, well, so Q is the respective projective quadric. given by the equation q equals 0. So then, well, so dimension of q is 2n minus 2, which can be written as 2 times 2n minus 1 minus 1. So then the motive of q is isomorphic to the following direct sum. It's r I from 0 to 2n minus 1 minus 1, where so r is indecomposable, and if we pass to an algebraic closure of our base field, then it splits into a direct sum of two Tate motives, of z and z shifted by 2n minus 1 minus 1 by this number. Well, so an example, if n is 3, is this picture. So this is well, and as I said, it's not so easy to find an elementary proof in the literature, but I know one. So let me explain it to you. You also will see how. So I hope you will see the connection between motives and width, so higher width indices in the proof. So we will use it. Well, so the proof consists of several independent steps. So the first step, so let us look at the Chow group, or even at the Chow ring of split quadrics. Well, so there is a special element, so H, it's so the generator of Chow 1 of Q bar. So Q bar means Q over K bar, so it's a hyperbolic quadric. So namely subquadric of codimension 1. So let's denote it by H. So H because of hyperplane. It's a hyperplane section of Q bar. So then we have powers of H, and well, so this is an element in Chow I of Q bar, and well, it's easy to see that H is rational. So H is defined over the base field. And if H is rational, then of course all its powers are also rational. Okay, just because it's the same, I mean, the subquadric exists always. So then there are classes of linear subspaces inside of Q bar. So there are L0, L1, and so on. So these are the class of a point, class of P1, and so on, up to the middle of dimension. So these are also elements in Chow I of Q bar. So they are not rational anymore, but they exist over K bar, because over K bar Q is split, so it's hyperbolic. And these elements form a basis for the Chow group. So it's very concrete. So H, powers of H, and classes of subspaces inside of Q. Okay, so moreover, yeah. So we can recover completely the multiplicative structure. So for instance, well, it's not quite true, but mainly 2 times Li, it's h into an appropriate power. It's not quite true, but because there are some problems in the middle, so it's an exception. But if you go more to the right, then there is this formula. So the only exception is the middle codimension. For the middle codimension, there are also formulas, but they depend on the dimension modulo 4. So I'm not sure I want to write all cases here, and also we will not need them in the proof. Well, so this is the first completely general observation that the Chow ring of a hyperbolic quadric is completely classically known. Well, so let's remember this. So now, since we look at a Pfister quadric, so its first Witt index is maximal. So this is again a classical fact from quadratic form theory. So I1 of Q is maximal. So i.e. it's 2n minus 1, or yeah. Okay, and this implies that the class of 2n minus 1 is defined of the function field of Q. Just by the very definition of the first Witt index. So over the function field of Q, there is a totally isotropic subspace of this dimension, but this is the definition of else. So and now let us draw some I call it generic point diagram. So it looks as follows. So let M be the dimension divided by 2. So and we consider the following square. So the vertical arrows are just extensions of scalars from the base field to its algebraic closure, and the horizontal arrows are the pullbacks of embeddings of generic points. So they are surjective by the localization sequence, by the localization axiom. Well, but then if we look here on the right, Q, so Q is a Pfister quadric, of its function field splits completely. So what is here is a hyperbolic quadric. The same here. So here we have the same group. It's an isomorphism here by our assumption that I1 is maximal. So now here we have this class L to n minus 1 minus 1. Since this is an isomorphism, we have also this class here. So it is defined, it comes from here. This map is surjective, there is a preimage. And by commutativity, this preimage goes here and goes to this element. So, and here, for this group, we have a Q-naught formula. Not for this, of course. So we can write everything completely in the basis with undefined coefficients, but in a very explicit way. So we can find an element here, which is rational, which comes from here, so lies in the image, which maps to here. So we know by this diagram that such an element exists. So let's write it down explicitly. well, there are many, but let's find one concrete. So it follows, so there is a rational element, so a rational cycle of the form, well, cycle on the product q times q. So it should map. So this is, again, remember, just embedding its projection. So projection, the first component. So it should look as L 2n minus 1 times 1 plus something from the kernel. So this is some sum of the elements of the form A times B such that the codimension of B is strictly positive. So here is codimension 0, and here some sum we don't know how exactly it looks like. So it maps to 0. It's general element from the kernel. But by step 1 we know explicitly the basis. So the bases are H's and L's. So we also know this element lies in Chow M. So it has codimension M on the product. Well, so there are not so many possibilities for A and B. So what can it be? It can be H, some power times H, or some other power, so the total degree should be M. So this is one possibility. So another possibility, so what can happen in that, it is L times H. Well, and it should have total degree M, so it means M is T plus, well, S's dimension, so codimension is 2M minus S. And T is not 0, because codimension is positive here. Or symmetrically, so it can be H T times LS, so with the same equation, but T can be 0 here, maybe. L times L is impossible by dimensional reason. It has too big codimension, so that's not possible. Well, so H times H is not interesting because H is rational, and we can subtract it or add, so eliminate. So this we can forget. So even if such a summand occurs here, we don't worry. We can eliminate it. So now let's look more concretely at this equation. So it implies that T plus M minus S is 0, and of course, so we should not forget that S and T lie between 0 and M, up to the middle. So there are not too many solutions, namely there is only one, just one solution. So namely, S is M and T is 0. So what does it mean? So it means we got a rational cycle which looks like well, so let's call it type 3. So we have a cycle Lm times 1 plus some coefficient times 1 times Lm is rational. So alpha is some number, some integer, which we don't know currently, but let's compute it. So we use a restriction co-restriction argument. So we know that Pfister quadratic splits over a quadratic field extension. So again, it's a classical fact from general quadratic form theory. And restriction co-restriction implies that twice any cycle is rational. Actually, you see the multiplication table 2 times Li is rational because of it's a power of H. But as I mentioned, there is a problem in the middle. But here, it's not the case. So co-restriction argument implies that twice any cycle is rational. So this means we can reduce this alpha to the value 0, 1, because just adding any even number. So it means, so without loss of generality, alpha is 0 or 1. And so assume it is 0. Well, if alpha is 0, so then, well, Lm times 1 is rational. But then we can transpose. The transpose is also rational. But then we can add. So sum of rational elements is rational. So we can assume alpha is 1. If it's 0, then well, so Lm times 1 plus 1 times Lm is rational. And the last step, which finishes the proof, I mean, you see, so far we used almost nothing. So the last step, so I think I don't need this picture anymore. So let's call this cycle, so let's denote it by rho, this sum. And let's take the cycles pi bar, defined as rho times hi times h m minus I, for I from 0 to m. Well, and then a direct computation, so claim, so they are pairwise orthogonal projectors. And the sum of them is the diagonal of Q bar. Well, actually, I'm not completely sure that the formula is correct, because maybe, so maybe it should be minus here. So I'm not quite sure, but something like this. So how to prove this? I mean, it's possible to do just using computer. It's just very elementary, because there is a completely general formula how to compose cycles of this form. And this, so this will be C times B, degree of AD. So this is the formula where, so I mean this times this and this should multiply. I mean, this is the usual product, A times D. Well, and degree is the usual degree. So it's from Chow of Q, in this case Q bar, to Z, which maps alpha to, well, the degree, I mean, the usual degree of alpha if alpha has dimension 0, so lies in Chow 0 of Q bar and 0 otherwise. So very often this is 0. Just using this concrete formula and using concrete multiplication table, one can really easily check that they are projectors, they are pairwise orthogonal, and their sum is the diagonal. Okay, so we are almost done. So I want to say they define these shifts from the statement. So the only problem, all these computations were over an algebraic closure over K bar, but we know they are rational. So they come from some cycles over K. But why should projectors come from projectors? Of course, it's not true. But there is again general principle due to Rost. It's called Rost-nilpotence. Which says that it's okay. One can live. So it's a Galois descent for motives, if you want. Well, at least for quadrics. So then it remains, there are indeed pre-images of Pi bar, which are projectors, and if we define R to be Q and pi 0, and then if we define Ri as Q and pi I, so this will be isomorphic to R shifted by I. And putting all together, we get exactly the decomposition of Rost. Okay, just really very short proof at the end of a quite strong statement which plays a very important role in the Milnor conjectures, in the proof. Well, and I think the final remark to this topic well, I did now some computations for quadrics, but there is similar technology for any twisted flag variety. So there are shells for arbitrary twisted flag varieties. And there are analogous results about the motives, but this is, of course, it's more tricky because, so first of all, there are some conditions which are automatically satisfied for quadrics and which are essential, which are not satisfied in general, and then one should require them, otherwise there are counterexamples. And one should, the Hasse diagrams are not anymore very practical then because they become huge. So one should change a little bit the language, but still you can do the same in general. So actually it's very surprising, I would say, that something which is true for quadrics is somehow true for arbitrary twisted, just because the gap is huge between quadric and arbitrary homogeneous, projective homogeneous variety, but still, it's possible to generalize. Okay, so and now I would like to pass to more algebraic applications. So I was talking to people here in the conference, so no one, everyone whom I asked did not know. So there is a very beautiful, but also a very naive proof of an old classical result about quadratic forms in I cube, in the third power of the fundamental ideal. Well, of course, there is a classical proof which uses nothing, just elementary quadratic form theory, but there is a Yeah, but there is a Matevik proof which I would like to present, which uses shells, which uses Stitz indices, which uses Rost motives. It uses a little bit of everything. So it's very short. So of course it's not, I mean, it's very strange because it's a proof of a very simple statement, but there is an analogous statement for IN, for arbitrary n. So due to Vyshek, Karpenko, and this is precisely how it goes. I mean, more or less, I mean, of course, much more advanced. So it will be part 4. So an application to the Witt ring. So remember we have Witt ring and we have a fundamental ideal which consists of even dimensional quadratic forms. And then let's look at the third power of it. So we take an anisotropic quadratic form from it, and there is absolutely, well, first of all, there is a question: what are possible dimensions of R, of forms from I cube, or more general from IN? Well, so there is a classical result of Arazon-Pfister, so it's called Arazon-Pfister Hauptsatz, which tells you that, well, of course, I don't want to take 0, so that the dimension of R is at least, well, so let's put here n, then at least 2 power n. So there is a restriction from below. So if n is 3, it means at least 8. Also, of course, they all should be even dimensional because I consists of even dimensional quadratic forms. But then one asks, is any other number possible? Well, always suitable fields. And the answer is no. There are further restrictions. And if n is 3, there is only one further restriction, namely dimension 10. There are no 10-dimensional quadratic forms in I cube over no field, I mean, never. So if R is I3, then dimension of R is not 10, and this is the only exception. So all other dimensions are possible over suitable fields. And in general, there is a result of, well, I don't know, of Vyshek or of Karpenko, a complete answer for any n. Just a complete list of all possible exceptions they mentioned. Well, so I would like to prove this using motives. Well, so Matevik proof. No, not of the Hauptsatz is about, so Hauptsatz tells at least 8, so 10 is not excluded, okay. And 8 is possible, it's Pfister form, but I would like to exclude 10. And 12 is again possible, but not 10. So there is a gap, okay. Or a hole at the beginning. Well, so again, so the proof consists of several independent steps. So I think I will start today and finish tomorrow, but the steps are completely independent. So let us look first. So let us forget about dimension 10. So let us look. Well, first of all, assume there is a 10-dimensional form in I cube. Just starting point. So dimension of R is 10. R is from I cube and is anisotropic. Well, so now step 1. So let Q Q be an 8-dimensional quadratic form, arbitrary, with the splitting pattern two. Well, always anisotropic. Q. And let P be any codimension one subform of Q. So Q is 8-dimensional, P is 7-dimensional. So then I claim, well, so I don't claim anything. Then first of all, it follows. Okay. So let me write it first. So then the motives of P and Q have a common direct summand. So P and Q have a common indecomposable motivic direct summand. So why is it so? Well, there is a general criterion, which is actually not difficult to prove. Well, to decide when this happens, that the motives of two quadrics have a common direct summand, namely, it suffices it suffices to show that so Q over the function field of P and P over the function field of Q are isotropic. So have a rational point. Well, so one of these two cases is completely clear, since P is a subform of Q. If over the function field of P, P has a rational point, but it's still a subform of Q. So this is obvious that this is isotropic. It's clear since P is a subform of Q. So this is more tricky. Because Q is bigger. But we know the splitting pattern. So we know that the first width index is 2. So this is I. So it means when we pass to the function field, we get 2 copies of hyperbolic planes. So a 2-dimensional, totally isotropic subspace. So, okay, and we leave, so Q lives in some 8-dimensional vector space. So P lives in some codimension 1 subspace, so 7-dimensional. So 7-dimensional subspace and 2-dimensional isotropic subspace have at least 1-dimensional intersection by this the Dimensionsformel. from linear algebra. So there is indeed at least one-dimensional totally isotropic. So it's since so the width index of Q over its function field is 2 by our assumptions, and codimension of P is 1. So there is a non-trivial intersection of this total isotropic subspace. Okay, so this is satisfied, so they have a common motive, and let's now find it explicitly using the technology of shells. So let's combine. So let me draw. So we need two pictures, one for Q and one for P. So for Q, so it's an 8-dimensional quadratic form, so 6-dimensional quadric. But it's not a Pfister quadric, so it has different splitting pattern. So then, so the first shell has 2 Tate motives, and the second shell has 2 Tate motives. Well, and we draw the connections. Okay, so it's somehow easier to start here. So they are connected like this, then this is connected with this, and this is connected with this. So now, if we so we know that inside of shells we can shift direct summands. So in particular, this point and this point, they are not connected. But maybe this point, it could be connected to this point, or could be not. So there are 2 possibilities. So it's not a complete Matevik decomposition. It's just a picture for connections which are which must be. Maybe there are more connections. But if you look at this motive, this one, when we pass to the closure, it will have, it will become binary. So namely, so Z with shift 0 and then 0, 1, 2, 3, 4, 5. And there is a binary motive theorem, which we will use now, and we will use it once more next time. So if n is a direct summand, is an indecomposable direct summand, of the motive of some quadric, so it does not matter which one. Well, but actually this can be generalized. It's not only for quadrics the case. So then, well, so n over the closure is isomorphic to Z plus Z shifted by 2L minus 1 for some L. It should be exactly the same shift as for Rost motives. And 5 is not of this form. So, indeed, it should be a connection. And again, by this principle of shifting, so the only possibility that this state motive is connected to this one. So it should be this connection. And just by the same reason, another one, this with this, I guess. So we have the Tate motives 0, 2, 3, and 5. So they belong to this. I mean, this is the picture for the complete Matevik decomposition. There is a motive, n, and it twists by 1. And n consists of Tate motives with shift 0, 2, 3, and 5. Okay. Now let's do the same for P, for the subform. So now something very strange will happen. So let's draw the picture. So it's odd dimensional, so it will be a chain. So it was Q. Now let's do it for P. So this is the motif of P. So it's 7-dimensional quadratic form, so 5-dimensional quadric. And they have a common direct summand, so that n. Okay, so 0, 1, 2, 3, 4, 5, and it should be 0, 2, 3, and 5. Okay, but let's look what remains. It remains that 1 is connected to 4. So we just proved that any subform of such an 8-dimensional quadratic form contains here in the middle, in the motif, a binary direct summand. Actually, the dimension is 1, 2, 3. So 3 is 2 power 2 minus 1. There is no contradiction. Not yet. It's not so easy. But we proved something interesting, that here in the middle there is this binary summand. And we will use it just very soon. So precisely this one. I mean, not the outer one, but the inner one. Okay, so this finishes the step number 1. Well, so let me formulate step number 2. And so now we will start with a 10-dimensional quadratic form from I3, anisotropic. So now we take any 3-dimensional subform in it. So it's a subform, so we can write R as ABC plus some 7-dimensional form. Well, 3 plus 7 is 10. And then we can define Q as P plus minus ABC. So then it will be an 8-dimensional quadratic form. And the claim is that this form Q, well, so first of all, you see P is a codimension 1 subform of Q, but the claim is that the splitting pattern of Q is exactly 2, 2. So we can apply step 1. So then, well, first of all, Q equals pi modulo I cube. So where pi is a twofold Pfister form minus b divided by a minus c divided by a. So two Pfister form. So it's 4-dimensional. And the splitting pattern is 2, 2.
Well, so I will show it
next time, so it's not very difficult. Actually, in the proof, also some beautiful classical results will appear, and then we will combine step 1 and step 2 and then get a contradiction. So that's the plan, at least for the beginning of the lecture tomorrow. So thank you for your attention. And,